Welcome back. As you remember from the last video, in this unit we're talking about applications of the derivative, and last lecture we talked about position graphs. Well, today we're going to talk about using derivatives to answer questions that aren't necessarily about position, but that still involve rate of change and first and second derivatives. In particular, we'll talk about projectile motion and marginal revenue. Before we get started with some examples, I'd like to talk briefly about a strategy, because moving forward this year, a huge skill for you is going to be to find the math inside of a word problem. We talked about it yesterday with those keywords, but we're broadening the context. So when you encounter a real-world problem, obviously you're going to read and interpret, and you always want to kind of identify known information and identify what the answer will look like. Things like units and variables can help you there. That's pretty normal for you. And then I want you to find the function. So there's going to be something that we're talking about, something that we're predicting, something that we're asking questions about, and that's going to be the dependent variable of some function. In some cases, the question might give you the function. In other cases, you're going to need to create the function based on formulas that you know or interpreting what's going on. But once you've got the function, then you can identify the calculus. The question that's being asked, is it asking a question that's going to require you to use a first derivative, a second derivative, etc. And then, of course, once you identify what the calculus is, the last step should be pretty easy. You just perform the operations that you identify. Let's take a look. We'll start with an example that involves some geometry. Find the rate of change of the volume of a sphere with respect to its radius. Evaluate the rate of change at r equals 5 and r equals 10. What can you interpret from these two rates of change? So this is, as it's written, just a straight-up geometry question, and I'm going to try and give you some more interesting questions this unit, but sometimes just to test your understanding of the concept, it's nice to start with a purely mathematical question. If it helps you to be invested in that kind of question, we can easily imagine why this kind of question would be important, because there are many things in this world that have a spherical shape and that might be changing in size. For example, the sun is a sphere and it's expanding as the sun gets older. And so scientists who want to study astronomy, or who want to understand what could potentially happen to our solar system in 1 million or 2 million years, are going to want to know how quickly the sun's size is changing and how quickly its radius is changing, what the relationship is there. Back to the problem. So in this question, to start out, we want to find the rate of change of the volume of a sphere with respect to its radius. When we talked about our strategies on the last slide, we said the first thing to do is obviously identify known information. Well, there isn't very much given to us here, but I do understand that my answer is first going to be a derivative function. Rate of change with respect to radius. A rate of change is a derivative. And it's going to be the derivative of a function that has a particular input and output, and the problem tells me what they are. The function that I'm starting with, the function whose derivative I want to take, is the function that measures the volume of the sphere using the radius, and that's my dependent and independent variable. What's interesting is that they don't actually give us the original function. So to start this problem, I'm going to need to come up with a formula for the volume, and the formula is going to have a variable r in it. As it turns out, the volume of a sphere is 4 over 3 pi r cubed, and in order to answer this question, you would either have had to know that or you would have had to look it up. Now that I have that formula, I can find the rate of change by taking its derivative, which just means multiplying the exponent in front and dropping the exponent by 1. Notice that when you multiply by 3, it cancels out the 3 on the bottom. And so the formula for the rate of change in this case is 4 pi r squared. And that's the derivative of volume, which is the rate of change of volume. And then to finish the problem, it says evaluate this rate of change at 5 as a radius and 10 as a radius. To do that, I just plug in 5 and 10 to the derivative function. At 5, we end up with a rate of change of 100 pi. And the units are a little tricky here. Units for first derivative is always a fraction, and the top unit is the unit of the dependent variable. So volume's usually measured in something cubed. And then the bottom unit is the unit of the independent variable. In this case, it would just be meters. And that looks like a funny kind of units, but we're saying this is how much the volume changes if we increase the radius by just a little bit. What we can notice by comparing these two is that when the radius is 10, increasing the radius a little bit has a much bigger effect on the volume. The rate is much higher than when the radius was 5. And that makes sense because when you're looking at a sphere, if it's already a large sphere, increasing the radius a little bit more creates a much larger volume than increasing a small radius. So one thing you may have noticed from this example is that we're actually going to need to rely on some geometry formulas. These are geometry formulas that you need to know and memorize. You need to know how to find the area and perimeter of all of these normal shapes. You need to be able to find the volume of a box or a rectangular solid. And you do actually need to know the formulas for pyramids and cones and cylinders, but you don't have to memorize each of them individually if you can just remember these two rules in green. A prism is any time you have a shape that is elongated. So like a cylinder is a prism with a base that's a circle. A rectangular solid is a prism with a base that's a rectangle. It's any time you extend this one shape all the way up. And the volume of a prism is always going to be the area of the base times the height. And so you can remember that and use that whether it's a cylinder or a rectangle or a triangular prism. Similarly, a pyramid or anything that has a pointy top, the volume of both cones and pyramids is 1/3 times the area of the base. For the cone, the base is going to be a circle. For a pyramid, it's a square or a triangle. And then you multiply it times the height. So if you understand how to use and apply these last two formulas, you don't have to memorize a million different things. When I say you need to know these, I mean I expect you to know them this week. A lot of them you should know already. They should go and cram, you should study them, you should be prepared to have me quiz you on them. If you don't know these by next week's lesson, you will be very sad and the problems will seem very hard. But they don't have to. Learn the formulas. Okay, let's move on to a non-geometry example. Vertical motion. Suppose a dynamite blast propels a heavy rock straight up and it has a certain velocity. And then the rock reaches a height of s equals 160t minus 16t squared after t seconds. We want to know how high did it go, what's the velocity and speed of the rock when it's 256 feet above the ground on its way up and way down. And then we want to find the acceleration. And when did the rock hit the ground? We'll go piece by piece. To start with, let's think about what we know. So we're given this formula s. This is the function. And what are the inputs and outputs, dependent and dependent variable here? Exactly, we're measuring height as a function of time. And in fact, sometimes if you can, it might be helpful to sketch. If you see this, this is a negative parabola. And if you think about at time 0, the function would equal 0. So we can kind of guess that this is going to be a parabola that's downward facing and goes through the origin. Something like this. And that makes sense if we're imagining a rock going up into the air and then falling back to the ground. So let's talk about A. A is asking how high did it go? Pull out those keywords from yesterday's video. If I'm asking about how high, what function am I interested in? Right, so how high is a question that we're going to use the original function for, because height is the original function. Now, in order to answer how high, I need to plug in a certain number for t into the original function. What time would that be? Yeah, we need to know the time when this function reaches its highest point. And this is where you have to be a little sneaky, because we're not given that time in the question. So we're going to have to figure out what time that is. How could we calculate what time this function has its maximum? Yeah, so this is basically just a critical point. If you look at it, the maximum is where the derivative is 0. So even though question A is ultimately going to be a question that we answer by plugging into the original function, I'm going to use the derivative first. I'm going to use the derivative to figure out the time when it reaches its highest point. Then I'm going to take that time and plug into the original function to figure out how high it went. Basically, I'm going to find the maximum. Here's what the work looks like. I start with the first derivative of position, then I set and I solve for time. This now tells me that 5 seconds after it starts moving is when this object reaches its highest point. The question's asking me what is the y value, so I'm going to take this number and plug it back into the original equation. And the work looks basically like this. Of course, feel free to use a calculator in these unless it says you're not supposed to. Okay, that takes care of A. Let's talk about B. In B, we're asked to find the velocity. You should remember that velocity is the first derivative. So we expect that in order to answer B, we're most likely going to be plugging into the first derivative. What's difficult is that the first derivative, what you're supposed to plug in is a time. And we're not given a time. So even though B is going to be a question that we answer using the first derivative, before we can do that, we need to figure out the time that we're going to plug in. Well, listening to what the question's asking, it's saying the velocity at 256 feet. There must be some time when the rock is 256 feet high. And this number being a height makes me think of the original equation, because the original equation is the height equation. So if I could just figure out what value of t would make this original equation equal 256, then I would know what value of t to plug into my derivative for b. Well, what I just described was the process of setting up an equation, and that's going to be the first step in part B. Again, in the long run, we're going to use the first derivative. Before we do that, we need to find time. We need to find the time when the height is 256. Mathematically, that means setting up an equation and solving for t. So I start B by setting the original function equal to 256, and then I'm going to solve for t. Solving for t means first rearranging this quadratic equation to get 0 on one side, then factoring out a greatest common factor, then factoring the inside trinomial, maybe using snowflake method, and from there I can clearly see the two solutions. So what does it mean that there are two solutions? Well, it means there are two different times when this rock has a height of 256 feet. And that makes sense, actually, because if you think about the path of the rock, it's going to have that height on its way up, and then again on its way back down. So if our two times are 2 seconds and 8 seconds, the first one represents when it has that height and it's moving up, and the second is when it has that height and it's moving back down, which is exactly what we're supposed to find. So again, the question's asking me for the velocity, which means I'm going to plug each of these times into the first derivative function. The work looks like this, and what you notice is actually the speed is the same. On your way up and your way down, the speed of the object is 96 feet per second, but the velocity is different, and it's different just because one's positive and the other's negative, which means the direction the rock is traveling is different. And that makes sense. It's supposed to be going up here and going down here.